Hello everyone, hope you all are doing well. After we have completed the first part of our tutorial related to deep learning for the satellite imagery, this is the second part of our tutorial where we are going to focus on the deep learning part of satellite imagery. There are lots of technical grounds we are going to cover in this second part of our tutorial. The second part of this video is start with the code where we have left in the part 1 of this video tutorial series. We start our work from here. That's where we start coding the unit-based model. One of the most important part of this tutorial is that we start our coding work by looking into the original UNet neural network architecture. We learn each and every layer and we code from line by line our unit model. And after each and every layer we have hand coded by ourselves. Once our model is ready and it is saved to the disk, we load that model to the Netron deep learning model visualizer tool where we validate each and every layer with its parameters, configuration, connectivity to other layers, concatenation, and everything else what we have done in our code, and we validate everything through the model visualizer and make sure that everything what we have done has been described in the architecture and created in our code. We learn how to add the Jaccard coefficients as our model evaluation matrix. We implement the Jaccard coefficients. Then after we learn the UNet model network itself by checking the model network using the Netron open source deep learning network visualization library. We review the full neural network as defined originally by the UNet creators, and step by step we follow each and every step as defined in this original UNet architecture, and we add each layer by layer in this tutorial, finally completing our model. After our model is ready, we add the loss function. The loss function we use for this model is the focal loss, which is an extension to the cross entropy loss, and we learn how to create the loss function by using the segmentation model and build our loss method as well. Finally, we compile our model, learn how to visualize the model as the plot image, and perform the training. Once training is completed, we get the model metrics with the loss and validation loss, as well as our Jaccard coefficients and the validation Jaccard coefficients metrics. And finally, by using the model, we perform the prediction, and in the prediction we use the original image and the predicted image, and we compare it side by side with the original ground truth. Further, we add diagnostics to our model training process where we add two separate classes, one plot loss where we learn the real-time model diagnostics by printing the model metrics after each epoch, and we extend our diagnostic class by printing two or more validation metrics, loss and Jaccard with the validation metrics, and we also see these values after each epoch. Finally, we download our model to the local file system and get ourselves ready to deploy this model at Hugging Face space in the third part of this video series, where we could take an image from Google Maps and use our model, and by writing the Gradio code, we could perform the prediction. So as you could see that there is a lot to learn in second part, but covering, as you could see, there is a lot to learn in this second part of our tutorial. However, you must go through with the very first part of this tutorial to make sure you understand everything what we are going to cover in this second part. In this second part of our exercise, first we will just review the code which we have covered in very first part of our exercise. First, I'm just importing the particular libraries as well as the install whatever was missing, setting up the min-max scaler, setting up our folder so that we could read the data. And now we are creating the image data set and the mask data set. All the images are going to be read from the Google Drive. So we are reading the images and as well as their masks. So there are total 945 images which we are processing after we have processed the input data. We are just taking a look of the random images in our training data set. Then we are processing the labels, defining the RGB to label conversion method, setting up the labels, setting up the labels array. Total number of unique labels we have, total 6. Now, rather than using the mask dataset, we are using the labels dataset to visualize our training images with mask. Total number of classes, we have 6. And at this point, we are creating the training as well as the test dataset by using the TensorFlow and sklearn libraries. Our training dataset is ready, and here are the image height, width, channels, and classes. And that's where we left our part 1. For those who are only watching this part 2, please, you have to watch the part 1, which is must in order to understand what we are going to do in this part 2. So because this part 2 is all about deep learning, so we are going to import the Keras library and various methods available in this Keras. So from keras.models, we need to import the model. As the model is a class here. In the next step, from keras.layers, so for every deep learning training, you need layers. So we are going to import bunch of layers. These are all classes. So we need input. We also need convolution 2D. Then we also need the max pooling 2D, upsampling 2D, convolution. So convolution. So we take the convolution 2D to transpose because that's for matrix manipulation here. And then I will be loading even more, but I just want to keep them two separate lines. Layers, we need to import. We also need to import the concatenation layer. So there is a concatenation layer, which is a method. We need to take the batch normalization class. We need to take the dropout. We also need the lambda class. So I will be importing the backend. So from keras import backend as K. So why I kept this in a single separate line? Reason is that because Keras is a high level model label library. So what that means? It means that everything related to deep learning high level building blocks, it is what covered by the Keras. The backend could be anything. Right now in this example, our backend is the TensorFlow. So all the backend calculation, when we say backend or when I say backend, it exactly means that at the tensor level calculation. So when the tensor level calculation, all the deep mathematics is going on, that is not covered by the Kera. Kera is just a high level methodology where these classes or these methods gives us the skeleton, what we want to do. But when it comes to processing the tensors, everything goes back to the backend. So that's why we are importing the backend here as K. So we will denote all the backend methods through K. But as soon as we are referring to the K, you can understand that the calculation goes deep inside the Keras backend, which could be whatever we have defined right now. By default, the Kera backend is TensorFlow. However, you can change this to even use the other deep learning libraries. That's the reason I have kept it separate line. In the next step, first we are going to set up our evaluation matrix. So most of the time, whenever we are building the deep learning model, the metrics similar to accuracies are the most used method. However, remember, this is the segmentation task what we are doing. And in our kind of problems, such as when we are recognizing the landmarks on a satellite image, so in that kind of task, we are going to use a matrix called IOU, or the intersection over union. Mathematically, it's the overlap divided by the union. So as you could see that the overlap, we are creating a matrix overlap. So if we have two metrics, we could get the overlap, and then we could take the union, combined data, overlap data, which is divided by the overall combined data. And then when you take this result, that is what gives you the intersection over union, which is also called the Jaccard Index. So we are going to create a function in our code that will use this data. And if you remember, this is what we are going to apply on our labels data. And right side image, which I have taken from the Wikipedia, if you are getting the overlap, which is exactly the union. So the overlap is the same value as the union, your IOU is going to be exact 1. It means it's a perfect match. However, if your overlap is just a 1% and the union is 100%, then division of 1% divided by the 100% will be the very less value. So that's the way you could figure it out, that when you are performing your training and then your results are coming out, the metrics will say that how good your training process went in order to identify the class. And the example is visible in front of you, that excellent results will be over 90% when the overlap area is almost similar to the area of union. So let's build the Jaccard function, or the Jaccard index coefficient method in our code. Define Jaccard coefficient, and for this, remember, we have to take our training data which we have already created. So we are going to take the y true and the y predictions. Remember, we need the y true and y prediction, that will be our input, and we need to use the backend. We will take the y true and we need to flatten them out, k dot flatten, and we are going to pass the y true, and that result will be the y of true flatten value. Similar to that, we are going to perform the k dot flatten, and we are going to pass the y of predictions, and this result is going to be the y of prediction flatten. So now we have got the y true and y prediction, and the intersection value will be the k. So let's take what our value is. So we will take the multiplication of flattening prediction, and we will call the backend. So k dot sum, we could say final value or final coefficient value is going to be the intersection divided by k of sum y true flatten plus k of sum y prediction flatten minus intersection, which we have calculated. And so that's what is really covers here. So let's take a look what it really gives us. So final coefficient value is the intersection divided by the all the flattens k sum prediction flatten. So this is what, and then so by taking the true values as well as the predicted values and then multiply them is going to give you the intersection. So we are dividing the intersection with the all the true flattening values. So true positive, false positive, and we need to subtract it from the false negative. So this is what our final coefficient is. And in order to complete this math, the best option is to use the 1 plus 0 here. And in this result, when we have, we can also make it plus 1.0. And that is what gives you the final coefficient value, and that will be your return. This is the math to generate the Jaccard coefficient, and there are several other tutorials available which will help you to learn even more about, if that is what your intention is, to learn deeply about the Jaccard coefficient. In the next step, we are going to build our model. So let's define multi-unit model. And here we are going to pass some of the parameters. So before we even start implementing our unit model method, let's take a look what the unit model really look like. This is the original architecture of the model, where you see this is the input image and then the max pooling happens. So this is the red arrow for max pooling. So max pooling, max pooling, max pooling, max pooling, and then here the upsampling. So conversion happening. So conversion, and finally this is the output segmentation layer. So we need to build a model which really follows everything all the way as described in front of you. There is a library called Netron, open source, you can download. I do have YouTube video which explains about Netron, how you could visualize any deep learning model using Netron. And here you can actually go to netron.app and take a deep learning model, drop on the UI that will load the model and visualize you. So here what I have done, I have already created a previous model for the same problem, and here I am using the same model and visualizing its content. So what you are seeing here is exactly what has been explained here, but this is the real actual model. This is the concept which was proven in the test, and that's what it's a visualization, the description, and here is the actual model, the .h5 file which is really being loaded. So as you could see that here the convolution happened, dropout, then max pooling. Similar to that, as you look into convolution is going to happen, then the dropout. So how each layer is going to be connected from its previous layer is visible here, and that is what is our exercise in this next step. Here we need to provide the number of classes. We need to provide the image height. This is our image height, image width, and we also need to provide the image channels. And whenever you are creating a model, it's best for you to provide the default values. So you already know that in case if the values are not there, model created based on default values. So the number of classes, you could say default is 5. The image height is 256, image width is 256, because this is what we already have. The image channels, we can say minimum default is 1, means gray images. However, our images are 3 channel RGB images. So these are the parameters of our model function. Then we need to define the input. So you could say input, thus your model is going to be defined, and input is going to be this input, which we are creating the Keras layer, and we need to pass whatever our input tuple. So input tuple will be the input height, width, and the channel. So input, image height, width, and the channels. So that is our input. So very first we need to create the convolutional 2D layer. Let's go ahead, convolutional 2. So we have already taken this. So this is our layer we are creating. There are tons of parameters we really need to pass, but we are going to define the minimum parameters. So as you could see here, that stride is already been defined earlier. Padding is already been defined. So some of these parameters are already defined. It means if we will not pass these parameters, the default value is going to be used. However, some of these parameters such as filter, kernel size, we have to provide. So let's start with convolutional 2D, 16 filter, kernel size is a tuple, so it's a 3 by 3. Then activation, we can also look into here, activation is set for none. So we need to provide our activation is equal to value. Kernel initializer we need to provide. So right now the default kernel initializer is the glow rot uniform. We need to change it to a normal. So let's use the kernel initializer. So whenever you are working on a deep learning problem and you are using the existing model, you are basically following what these researchers have already spent countless hours of their time to build the model. Then after, we can look into the padding. If the padding is defined, you can always look into the layer. So the padding is valid. So we need to use the padding as the same. So that is our very first convolutional 2D layer. So that has defined. So we need to set it up into a particular object. So right now it's a C1. And whenever you are define a layer, you really need to pass, because this is our very first layer. So we need to pass our input. So the best way to set it up, so you could say the source input is our this input, and this input is going to be used as the input for our very first layer. So this is what we are creating. So everything what has been explained here. So you see this, a convolution is defined. It's a 3x3 kernel and our activation is ReLU. So we have used exact same method. So convolution 3x3 ReLU. We have used 3x3 ReLU. And now we need to follow the same method here. This is what has been defined. So now we need to set up the dropout. So you can say dropout. So that is also defined here, dropout. So dropout, we need to set up a dropout rate, that at what rate we would want to drop out. So it could be like you want to drop out 20%, 30%, 40%. So whatever percent you want, you could say that, okay, let's drop out 0.02. It means we would want to drop the 20% values here. We need to provide an input for this. So the C1 is the input, and then the output of this will also be the C1. So what we are saying here is that create a convolutional layer, pass this input, and then after take the drop out 20% of the data based on C1, and then whatever remaining is this C1. So now we have the 80% of our data going forward. So some of these layers have that many neurons we are dropping. So that's the dropout. And if you would want to perform the experimentation, that is the place where you can perform the experimentation by changing these value to a different value, because the original network was designed for biomedical images. So when we are applying this network for satellite images, on tomorrow you are trying to perform something total different. For example, agricultural images, crop detection, fruit detection, anything, or the disease detection in the trees, you could actually take the same network model and try to play with the certain parameters and see what is going to help us to maximize your IOU or the Jaccard coefficient. Similar to that, we are still using this. So one more convolution layer before we are going to max pool it. So take this. So this is our another convolution layer. So we perform another convolution here, and our parameters are exactly the same. We didn't change anything. The input is C1 and then the output is C1. So we perform another convolution here. So two convolution happen. At this point, we need to max pool it. So let's max pool it. Let's look into the max pool layer. So here, see, the default pool size is 2x2 with no strides. So we are going to use the exact same tuple. So 2x2, and it will take the C1 as previous layer as input, and it's going to create the P1. So that's our first block as explained here, and then we perform the max pooling. And again, this is just, I'm using somebody else work on satellite imagery. So some of the values has already been validated by them. That is what gave them better results. So that's the reason we have created this very first block. And here, as you could see, that first the filter was 6464. In the next step, it became double. So it became 128, 128. It means in our example, whatever our filter was, now we need to double it out in the second layer. So this is our C2. The P1, which is the max pooled output, is going to be the input here. And this should be the 32, because it shows that we need to double it out from whatever filter we have used, because the 6464 was for biomedical images. And we have used the 16 to start with, and I'm using somebody else's work. So if they have started 16, so that's the reason I'm putting 32, 32. We are not changing because the convolution is defined as a 3x3 kernel. So we are keeping that. Activation is relu. Kernel initializer is still the same. That's became C2. Now this is going to be C2, C2. We are building the same here. So that could be the C2. The input is going to be the C2. Whenever you are copying and pasting, make sure everything is being correct because it has to be logically understood in your brain before you are performing any model building. And then here it's going to be the C2, which will generate the P2. And that is what we have completed this one. Now you see that filters are doubling here. So we have to follow exact same way. So now the third, and remember the max pooling and then max pooling. So we are doing exact same way. So this will become over C3. The input is going to be the P2. 64, we have doubled the filters. Kernel is keeping the same. Dropout is same. Now it's became C3 every line. So P2, C3, it became the C3, became the C3. Input is going to be the C3. Sorry, filter has to be doubled. And max pooling is the P3. Input is going to be C3. And that's how we got up to here. Let's build the C4. The input is P3. 64 became double. 128. That is also, so 128. Then became C4. Dropout is C4. 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 128. And then finally the C4, and that will become the P4. And in the next step, as you could see here, that the max pooling is not here. However, at this point, the convolution is happening, and this is the blue for convolution, and the kernel size is doubled, but then after not doubled. So it's keeping the same. So we need to go from here after max pooling, we need to go to convolution with the double of filter from here, but keeping the same. So let's define the C5. 256. Input is P4. The dropout C5 became C5. So that is what we have covered this. Double it. Then we just need to perform another convolution. Same, the input is going to be the C5 and the result is still the C5. That's the way. So we are moving this direction. At this point, we have covered up to here. Now we need to go and start moving up. So we need to do the up conversion. So we are going to move from this direction to direction, and we need to hit back to our output layer. So let's come back here. So convolution to transpose. So we have already imported that method. So half of the previous filter. So it's a 128 tuple is going to be 2 by 2 as explained. 2 by 2 here up conversion. So that's the tuple. Then we need to set up the strides. So let's see what the strides are defined. The strides are 1 by 1. So we are changing strides to 2 by 2. Padding is valid. So padding is going to be the same. And that will be the C5 as the input. And that is going to be, because we are using the upsampling, so we just call this is U6. So U is for upsampling and 6 is our order. And next we are moving here. So we need to concatenate these values. So the value of U6 is going to be the concatenation of U6 and C3. Sorry, C4. Yep. So C5 was the input. The concatenation is the U of 6, this, and the C4. Keep in this way. So we need, oh sorry, this one we are doing at this point. So we need to go 3 more layer up. Perform the convolution again. So let's take this is the convolution 128 as the kernel, and the input is going to be the U6, and that became your C6 because it's a convolution. Let's use the dropout. C6, return will be the C6, another convolution here. Which is taking the C6 and returning the C6. So we have got the C6 covered. Now just keep doing the same thing. And as we are growing, we just need to keep reducing the same method. So I will take this whole block, paste here. It will be the U7, which is taking the C6. 128 will become the 64. Everything is same. At this point, the U7 is a concatenation of the U7, and this will be the C3 now. Remember, up. So that's what we got, C3. C7, input is U7. Filters are half, 64, active same. It became the C7. Result is C7. Input here is going to be C7. Everything is same. Filters became 64. The result became 67. That's pretty much, you go top to bottom, but you know where the changes are. And as you are moving further, make sure keep implementing the changes. Next block is going to be the U8. U8, 64 will become the 32. Input is C7, U8, and C2 became U8. This U8 is the input here. This is 32. Generate the convolution layer 8. This 8 is the input for the dropout. Generate still 8. This 8 is the input here. Keep going same way. Reduce to 32, which is the C8. We need to go back to 64. Means we started from 16, so we have to be 16 here. U9 convolution, which is 16, 2 by 2, taking the C8. Now the U9 concatenation of U9 and the C1, and at this point U9 is the input here. Keep going, became 16. Filter C9, dropout for the C9 is the C9. Finally the C9 comes here, come inside, and convolution for the 16, and that is the C9. So C1 is our first convolution, and here we are transposing, concatenating. So we are back to here. Now we need to define our output. So one thing I just wanted to show you in this concatenation, when we are performing the concatenation, the default axis is -1. So in the concatenation, you are performing you are giving the input array, and then the total number of inputs you would want to perform concatenate, and then the axis is -1. And because going further, we do not need to perform any further concatenation. So rather than using the default, we are going to perform the concatenation on the axis 3. So we need to set the axis 3 here. Now it is the point where we could generate our output layer. So output layer is again the convolution. So output layer is the convolution here. As you could see, this is the output convolution of the kernel 1 by 1. So convolution 2D, and remember the first parameter is going to be number of the classes. So the convolution is going to use the input parameter, total number of classes. The kernel is going to be the 1 by 1 as defined here. The activation is going to be the softmax. Why softmax? You will find on internet tons of tutorials that for the classification task, the softmax is the best activation. Please go through and learn more about it. The input is going to be the C9, and that is what is going to generate our output. So we could say this is our outputs. So we have created all these layers for our model, and now we could define our model. So model is going to be the Keras model, which is going to take the inputs and outputs. So inputs is going to be the inputs, outputs is going to be the outputs, and whatever it is going to be returned as a model. Let's see what is this warning here. Input is not defined. So actually just call it inputs, that's better. So because inputs, and that's a source input, we have passed source input to here S1. So that's the reason, because now you got an idea that why we really change it, because that way we know what is being input. So this inputs is actually the inputs here. So model inputs, model outputs, output has gone through with all the transformation here. So inputs and the outputs, and that's your model. Let's define our method. Let's define our metrics. So metrics are going to be the accuracy and the Jaccard coefficient, which we have defined earlier. So these are our metrics. Define the get deep learning model, and that is what is going to return our this model, where we are going to pass all of these parameters. So our parameters are these. So let's this, and these are the default values. So we need to set up our classes. So remember, we already have defined our classes here. So these are the total classes: image height, image width, image channels. So if I take this value and I print it again here, input channels, that is what. So that's the definition of our model. So whenever we call this get deep learning model, it's basically call this method and pass these parameters. So we don't really need to pass again. So this is easier for us to call the model. So now we could say the model is equals to get deep learning model. We have found some error. So our concatenate layer requires input with matching shape. So we could look into where the error is coming from. So if you would want to debug this problem, there are a very simple way to solve this problem, is that what you do, you actually reduce the number of layers. So what you do, you come here and you take this whole code, comment it, and create a temporary output here. And temporary output you are creating based on current. So your currently is a P1. So just use the P1, run it, then run it, and there is no error. It means that is right. Now you enable another one. Now your P2 is output. Use the P2 here. Define. So far is good. Then you come back, enable the P3. Use the P3 here. Okay, so far we are doing good. Enable the P4. P4 is okay. because error is with concatenation. So definitely it's gonna be coming next, but I have shown you how you could debug the problems. So now your output is C5. That's here, C6. C7. Let's come to here, C8. Let's come to here. So last one, let's use the C9. And that's where, so problem is in very last layer. So let's take a look. So we do not really need this, so we can keep original one. So let's take a look into the error. So the concatenation is happening and it says that the two layers which we are trying to input in the concatenation method, one is 512, 512 by 16, another one is 256, 256 by 16. So let's look into what we are concatenating. So we are U9 plus C1. So U9 is this, which is this layer, and then the C1 we can look into here. So C1, and here we are C2. So C2 is this is the error. You see that we are referring to P1 here, but this should be the input for this one, and that is the problem. Now if we define this correctly, then we call it, we should not have any problem. And that's where our model is defined. If we look into what the model really look like, you could get the details about model. You could say get config. Here is the model configuration. And if you take this whole thing and you dump into text file, you can get a lot more information related to your model. And that is very good way for you to look into. And most of the time, these utilities, they actually dump the config and then use the config to generate the structure like that. So I will go ahead and I will keep it. Now we need to figure it out what loss function we are going to use and how we are going to calculate it. So the loss function we are going to use in this project is going to be the focal loss. And focal loss is just an extension to the cross entropy loss. I would suggest you to please look into these keywords at internet and even go more deep into it depending on how much information you would want. For the sake of this workshop, I will show you how we are going to calculate the focal loss. So first, in order to generate our focal loss, we need the dice loss, and the dice loss is generated based on the equal class weight. So first we need to set the class weight. So for example, if we have the 10 classes, our equal weight will be the 0.1. That will create a 1 total. If we have 100 classes, then the weight will be the 0.01. In our case, because we have the 6 classes, remember we have building, water, land, vegetation, road, and the unlabeled data. So for that reason, our equal class weight is going to be the 0.166. So we take the equal class weight, and using a particular segmentation method, which I will be showing you, we will generate the dice loss. By using the dice loss, we are going to convert this whole dice loss into the focal loss. That will be the categorical, means the focal loss for each category. And finally, focal loss is going to give us the total loss, which is nothing but the combination of dice loss plus 1 times of focal loss. Because focal loss is going to be categorical for each category, so multiplied by 1 and then combining or summing up it with dice loss, we are going to get our final loss function that we call it total loss. Why we need it? We need it because in some of the images, there might be a very small spot of a certain class. That class could become the minority class because it might have the very less impressions against other classes. Because if you are trying to use the satellite data, you might find a one particular car somewhere here if you are identifying the car, or you are identifying a particular object such as the playground or a particular structure in a playground. So for that reason, using total loss function based on cross entropy loss is going to give you the higher chance to detect the particular class. That's why we are giving the equal weights for every class. No matter what the class distribution is in our mask data, still the every class starts with the equal class weight. So now let's calculate our total loss function in the Jupyter notebook. So first, let's define the weights. So I will create a tag here. Weights is going to be, because we have 6 classes, so it's very easy for us to create a very simple weight. So 0.166, and for 6 classes is a 6 time. If you have lots of classes, then you need to write a function 1, 2, 3, 4, 5, 6. So these are our weights. Now I will show you a particular library for segmentation model. So that is called segmentation model. Segmentation models with pre-trained backbones for the Keras and the TensorFlow. So we are going to import this library. So actually we need to really install it because that may not be available at Google Colab. So let's see if we could import it. Segmentation model is not installed, so we really need to install it. So we will come at the second part where we have started. We will install pip install segmentation models. Let's use the -u. So segmentation models is going to be installed in this Jupyter Notebook runtime environment. Ability to call the segmentation model. It is using the Keras as our framework. So now we need to pass the weights. So we need to pass the weights here. So we could say that sm DOS losses dot dice loss. We need to pass the weights, and that is what is going to generate the dice loss. Now we have the dice loss, so we need to generate the focal loss. Sm dot losses dot categorical focal loss. So the total loss is equal to dice loss plus 1 times of focal loss, and that is your total loss. So that is our loss function, which we are creating using segmentation model library and going to apply in our machine learning training. So now we have metrics, we have loss function, and we also have our model. It means we can go ahead and compile our model. Model compilation. So we need to import the TensorFlow. So import TensorFlow as TF, and we need to set up the backend session. So tf.keras.backend.clear session. At this point, we can go ahead because our model is already defined here, model. So we could say model.compile, and model, the compilation need minimum 3 things. We need to have the optimizer, and you already know for classification, Adam is the good optimizer. Next, we need to have the loss, and our loss is just, we have created the total loss, and our metrics, we have just defined our metrics, which are here. I just want to make sure accuracy and the Jaccard coefficient. Our model has to be compiled. Model is compiled. After model is compiled, you could generate the model summary. Here is your model summary, which is similar to this information. If you would want to dig into almost 2 million parameters. And now we can go ahead and create the training part. So you could say the model history is equal to model.fit. Looking into the fit, we need to provide the various parameters. So we need to have the xtrain, first parameter. Then we also need the ytrain is as a second parameter. Then you need to provide the batch size. I'm just giving some parameter, then I will explain. Verbose means explain it as much as you could. One is true. Epochs, I will use 10 just to start with because I had to explain you a lot. So the model performance is not in question as of now. Explanation is needed. Validation data, we need to provide tuple. So we have the X test and the Y test. So train was given validation data. Shuffle, do not shuffle the data. Okay, so it must be the false. So the key parameters are defined. So remember, we do have about 945 total images when we have started. We can validate it. So actually 803 input images. So if our batch size is that, so 800 divided by 16, and you are going to get around 45 to 50 total iteration in every epoch. So if we try to run this code, epochs is 10, it means it's going to run the 10 time. And for based on batch size, the 16 images will be processed each time. So depending on how many images we need to go that many iteration. So let me run this code. It's a first epoch. So we hit some error, and looking into the error, there are so many ways you could figure it out where the error is. So look into the code, how we can understand this very well. So here is our the segmentation model. So it means that this somewhere in this segmentation model library where this error is originated. So wherever we are using the segmentation models, we need to make sure that's where we need to look. And if we look into the generation of the code, is the training started from the Keras. Call went to segmentation models. In the segmentation models, trying to calculate the loss. So wherever we have used the loss coming out from the loss.py. So technically we have used the segmentation model here. So that is where the problem somewhere lie. So the sm.losses.dice loss, we can look into here what this class is, and definition of this class looks like it takes the parameter where arguments, class weights, class index. So let's make sure that we are providing this value as a class weights. So if we take this, so weights, now focal loss, so total loss is calculated correctly. So that was the class weight. So let's run this code now. So if that didn't solve the problem, I think I got the idea. I made a mistake when I was installing the library here, segmentation model, and this is the problem. Remember, I use underscore here, it totally changed the library. Looking into the library, it must be the dash segmentation model, and it asks us to use the latest one. So let's come back here, replace this code with the correct one, reinstall it. So at least we know the problem was at the segmentation models function. So that was focused over there, and it's asking us to restart the runtime in order to use this. So I will go ahead and restart, and I will just jump back to at the same place where we were there. So I have to restart this runtime. So the segmentation model has been installed. And I know this problem is because it's expecting us the keras.engines.utils, which is the latest code. So the problem is that we should not be installing the 0.2.1. We should install the base version, which is the release version. And it's using the 1.0.1, not the 2.1. And that's what is going to work with us here. Okay, at this point, now if we import, it should work. So it's using the Keras framework, dice loss, focal loss, and finally the total loss. So remember when we were installing with 0.2.1, that's where the problem happens, because the code which we are writing has the dependency on version 1. After that, importing the TensorFlow model summary, model history, and we should not hit the problem. Our first epoch is started. It's right now calculating that how many iterations we need per epoch. About 805 images divided by 16, 50. 51. It needs the 51 iterations in order to complete the each epoch. I am not sure if GPU is enabled here. So there is no GPU enabled. That's why it's going to take really long amount of time. So it's better to get the GPU enabled runtime if we could use this free version of that. If we are lucky, yes, new runtime is going to be created for the GPU one. And I will just jump back to exact same line here, and I will not show you anything, but I will reset everything and I will restart and I will come back here again. So we are back at the same place with the GPU. Now I will start the training, and with the help from Google providing us a free GPU, we should be able to get our 10 epochs done quickly. As you could see, the number is running fast, and that's the magic of GPU behind us. At the given time, because we have the verbose 1, we are getting the loss function value, the accuracy value, as well as the Jaccard coefficient. So these 10 epochs should be done really very quickly. So all the 10 iterations are done. Now we have our model history. So we could actually generate some plot. History A is equal to our model history. So we are keeping the model history object as it is, and we will work on history. So we need to get the loss. So history A dot history, and if you check, you will get all these values. You could see that there is a loss, there is accuracy, there is a Jaccard coefficient. So if you would want to get only the history of loss, you could get the loss here. So that will become our loss, be only once. And looking into the loss, that will be an array. So you can get all the loss value started from 0.99, only 0.93. So only 10 iteration. If we would have gone all the way to 150 iteration, we could have got a lot more deep inside. Now we can look into the validation loss. So we can take the same value here, and we could say, remember I have already shown you. So let me keep this in memory. So now you see that if you would want to get the validation loss, you could use this validation loss and you call it validation loss. You print the validation loss. So you are getting the validation loss. Now you can say that how many epochs you have. So whatever the epochs we had, we need to plot them out. So the total number of epochs is going to be the range of, we start from 1, and the length of the loss result. So there will be 10. So it's a 10 plus 1. So it is that way it became the dynamic value. So it's 0 to 1. So 1 to next. Now we can use the matplotlib. So plt.plot. We want based on epochs, based on loss, y, and the label is going to be the training loss. Let's plot another one where we want the epochs, but other will be the validation loss for the R, and the label is going to be the validation loss. Let's show it. At least we can get quick. Here is our validation versus the training loss. Add some few more. Title, X label, you have epochs. Y label, you have both losses. Make sure the legends are printed. So you are seeing the training and validation loss. Yellow is for training loss, red is for validation loss, and those for 10 epochs, this is where the values are. Now we need to get same values for Jaccard coefficient and the validation Jaccard coefficient. So let's come back here. So I'm just gonna keep it here for a while. Take this whole code, paste here. The values is going to come. So first we need the Jaccard coefficients, then we need the validation Jaccard. So that gives us both two values. Rest is going to be the same, and the only difference is going to be here is to the training IOU and the validation IOU. So this value will be the size of Jaccard loss, validation of Jaccard loss. That's where your training versus validation. Remember, our target is to reach the 1, because the once you reach the close to 1, that's where your validation should be the best one. So here we need to go from 0 to 1. Here we need to go from higher to lower. So now I will go ahead and set the epochs for 100. So at least we are going to have a more performant model, which we are going to perform the prediction and also going to save to the disk so that we could use this model to deploy at Hugging Face in the part 3 of this tutorial. And I will start this training and I will come back to you after these 100 epochs are completed. Now we are closing in to our training. 98, 99 epochs, 99th epochs is going on. So we just are just one away from completing our whole training. And you can always look into that where you started for your loss, accuracy, and Jaccard COP to the validation parameters for the loss, accuracy, and the Jaccard crop, where you can get an idea that we started from almost one loss. Jaccard was started from 0.33 and validation accuracy was about 0.7, and we go all the way down. We could look into the very last one here. We could say that we 0.36 to 0.74, almost double. Here we have validation accuracy started from 0.6, 0.86, and the validation loss started from about 0.99 all the way to came all the way to 0.91. And if you have more RAM, more time available, you can actually go this run for about 250 to 500 epochs. You are going to get even much better results. Then we are creating the graph. Now you could see that our training versus validation loss for the 100 iterations is much better than the 10. And here is the IOU. So we started from 0.3, we went all the way for the validation is red point here. So this graph looks much more impressive. It means we have done better job here. And same thing with the validation loss. We started from here and we came here. So validation loss is not that much, and the separation is getting bigger and bigger. So we could get an idea that there are some parameters we really need to tweak in order to get better results. So I think experimentation is needed when we are building our layers and try to play with some of these dropout percentage and see that what our rates are. And something can be adjusted here for better accuracy. Now at this point, check the model history, the parameters, 100 epochs, and each epoch has been calculated for the 51 steps. It means that for processing about 803 images based on 16 batch size, total 51 steps was taken in each epoch. So now we need to generate the predictions. So if you would want to get all the predictions we want, we can actually pass whole the test data. So you could say the model.predict, because the model is one has the architecture and has the whole network. So let's see what is inside the yPredict. Here what you are seeing is that you are seeing the coefficient. So let me see the length of yPredict. Length of yPredict is 142 because our test data has 142 images. Here we have 142 test images. So the prediction happen on all this whole X test object, which is the list of all the test images. So now we got the Y of prediction. Now we need to figure it out that for the prediction, what was our maximum? So in the Y prediction, we need to take, so we could use the numpy. So numpy.argmax, very popular method. You pass your Y prediction for the axis 3. That is going to give you the argmax of this Y prediction of argmax. Let's take this, check it out. Again, you can always check the length, all 142 values, Y prediction. We have the predictions for each image based on all the classes. So it takes the maximum prediction and it uses the label. So Y prediction. So depending on whatever it is from 0 to 5 images, so it's say 4 or 1. So it tells that depending on our label, what are the classes it's being predicted in our given image. Now if you need to perform the for Y test, so you can take Y prediction. And here you could actually say, I would like to have the Y test data, and that will be your Y test argmax. So what was the predicted and what was in the test? Now it can compare. So for example, looking into very first, it's a 333,111. If we look into very first one, it's a 111. All one were predicted, but it was actually 3 here. So now if you could compare between these two, you will get a better idea what was being predicted versus what was the actually in the test masked images. So rather than looking into that, we can actually compare everything apple to apple. Means we can compare the masked test image and the mask predicted image and see how the results are generated. So let's perform that now. So test image, we are selecting, so it will be the X of test, and let's use the very first image. We will create this dynamic later. So ground truth image is going to be the Y test argmax of the, so actually let's use this test image number, let's use the 10. Then the test. So whatever this test image is, so let's take this test image and expand its dimensions. So np dot expand dims test image by 0. So that is what your test image input, and prediction is going to be model dot predict test image input. The predicted image is going to be take your prediction, perform the same np.argmax, same axis 3. Okay, so we have this. Let's run here. You can see the predicted image. So predicted image is this. So what we need is that we need to actually take this predicted image out. So we could say that predicted image equals to predicted image of 0, slice. And if we have that predicted image, let me do this way. So now you see that predicted image is, this is our predicted image. Let me have before and after, because of you cannot print two cell, so I have to separate them in two cells. Okay, so there you go. Run, run, run. Initial predicted image. Now that's the predicted image. So that's the reason we had to perform this slicing operation. So now you got an idea. So I will go ahead and I will remove this cell and I will move this back to here. So this predicted image is, or you can actually take this whole thing and you can slice it here. They both are same. We do not need this. Now we need to create a plot where we could show these images. So if we take plt dot show and we have the ground truth image. Let's run. Oh, sorry, plt.im show. That's the ground truth. Let's create the test image. So this was the test image. So this is the image for the test image, and then we need to do the predicted image. Here is the predicted image. So you can get an idea that this was the ground truth and this is what we have predicted. So we can actually put all these three things in a same line using the subplot of matplotlib. So I can create a method here, plt.figure we have created earlier in the previous exercise. So we can say figure size is 14 by, is a tuple 14 by, I think it was 14 by 8, plt.subplot. So remember, if you need one plot, sorry, if you need two plots, so you could say 1, 2, 1, 1, 2, 2. But if you need the two plots, so you will use 2, 3, 1. So we can say 2, 3, 1. That's the subplot. So plot dot subplot 2, 3, 1, plt dot title, and that will be your original image. And then where you are going to show this guy. Then another subplot 2, 3, 2. So original image, that was the original masked image. 232, and that is going to be the ground truth. Then here is the predicted image 233, and it will be the predicted image. Run it. Let me delete this, delete this. So here are all the three images which we have. Now we can randomize this test image. So random.randint, and then it will be the 0 as I start, and the max will be the length of our X test. Run it, view it. Source image, here is the water body, green area, the constructed area looks like houses, and the road, and that's where you can get an idea that original, and this is what our predicted image look like. So you have good understanding of how your model is predicting, and you can visualize it in real time. In the next step, we are going to save our model to the disk. So model.save, and you can provide the location. So because we are using the collab, so model will be stored in this content folder here. So I will call it satellite segmentation. I call it full model.h5. Save it, close it, open it. Model is saved here. We could do ls.lah. We can get the size of model, that is about 23 meg. Now I will take this model and I will download to my local file system. So it's saved there. So we will be using that model from here to Hugging Face for our deployment. So download, and it will take few seconds to minute to download that model from Google Colab runtime environment to my local file system. And that progress bar is telling me what is going on. The model is being packaged and downloaded locally. So model has been downloaded to local file system. So even if we lose the runtime environment, that should be not a problem. So before I go and add the diagnostics, I will go ahead and I will save this Jupyter notebook to the DeepWorks repo where we have already sent the part 1 of this notebook. So save a copy. So I just call it base. So that's the base version, and then the diagnostics version, I will just call the diagnostics version. So base is available here, and the full code, what we have covered is all here. Okay. Now let's go ahead and add the diagnostics part in our training process. So I will keep the diagnostics for only 10 epochs. So that will be easier for us. So for example, whenever we are building this model, we want to visualize it. So in order to visualize, there is a library called the Keras. There is a method called the plot model. So from keras.utils.visUtils import plot model. Okay, so that method is available, and then you can use this plot model and you can pass your model. So our model is this. Then you can say to file, means where this model is going to be saved, it will be in the file, and then we just call it satellite model.png, and that's a plot png, and you can say show shapes equals to true and show layer names. So looking into this plot model method, show shapes and show layer names. So show layer names equals true. Let's run it, and it's taking this model and generating a full image of whole network. So that is one really very good way for you to visualize your model by using the built-in Keras plot model method. We are visualizing the model with Keras. That's a one diagnostics method, and you can experiment with various permutation and combination of true and false. And in the next step, whenever we are going to perform this model.fit, there is one more option, and let me show you what it is. Looking into the fit, you will see there is a method called the callback. Whenever this training is going on, you can connect a particular external method through the callbacks. So we are going to create a method called the callback here, and that method we will integrate in our training system. So that's how you are going to get the diagnostics data from your training process. So let's create a method called class plot loss. So it's just called the, and this class, because we are going to connect this class with this method, and because this is a keras method, so there is a type of object you need to define. It's a keras dot callbacks dot callback. So that's how the connectivity between this method and this method will be defined. So there is a method in this callback type, which is the on train begin, when the training begins. Self logs are nothing. So that's a first method. So self dot I is equal to, there are some already directives you can download from the keras.callback. So if we look into here, so you see that we are setting the on train begin, so on when the training is start, and then we need to perform the on epoch end. So every epoch, so depending on whenever you would want to get your result out, so we are going to use the on train begin, and we are also going to define the on epoch end self colon epoch, whatever the epoch ID is, and logs are going to be the empty on epoch end self dot logs dot append logs. And then this class we need to create an object, so we will call it plot loss object, which is of the type plot loss. And when we just run it, it's not complete yet, but I'm just showing you that, oh sorry, we need to define the keras. So we need to say import keras. Then we also need to make sure that we are doing the inline matplotlib. So matplotlib inline, that is needed. And we need to from IPython display import clear, because that's how we will be able to generate the animation kind of effect. Plot will create and then plot will be cleaned. So keras is there. It's not complete method, but at least it's going to give us the completeness. And then we will take this plot loss and we will integrate with the callback here. So callbacks is equal to plot loss. Now we need to complete this method. Okay, so I have already got this pre-code written. So here we are using the loss, validation loss. We can change it to other values as well. And here is the full. So I have copied and pasted the existing function. So you are getting the various loss and validation loss values, and we just need to make sure that our model is generating loss and validation losses. If it will not generate, we will not be able to get it. So here you see that our model does generate the loss and the accuracy and the Jaccard coefficient. Same, it will be the validation loss, validation accuracy, and validation Jaccard coefficient. So we could plot any of these. So let's make sure it's there, and then we can run this 10 iteration and see what happens. Oh, comma is needed here. Let's get the first epoch completed, because we have made the on epoch end. As you see that once the epoch end was generated, we have seen a new graph. Now you see that for one iteration, the epoch for the loss and validation loss is being printed, and then print is happening at every step. So this is how you could generate the diagnostics data for your deep learning training process, because we have 10 epochs. So it is going to give us the 10 epoch data, and you could change these validation loss parameter to Jaccard coefficient and the validation Jaccard coefficient. So it prints and it clears it and it replotted. So that is how you are going to get this animation coming out. So this is the very last epoch, and as you see here that this whole area is being reshuffled. So you are only going to get the very last epoch result, because we are keep clearing the output also. So now you have got the results for the 10 iterations. Next, we could actually take this example and we could use this Jaccard coefficient. So let me keep it as it is. For the, we need to get the, so it will be the validation Jaccard coefficient. So self dot validation will be the Jaccard coefficients and the validation Jaccard coefficients. That is what we have added. Similar to that here. So we need to say the Jaccard coefficient and the label is going to be the Jaccard coefficient. Here will be the validation this, and then that will be the parameter for it. And if we run this, run again for this method, now we are going to see the value related to our Jaccard coefficient. So because our free version of Google Colab environment crashed, so let me restart and I will come back here and I will perform. So let me run all the way up to here. And as we learned earlier that the graph is going to be printed after the first epoch is completed, and we are going to see the Jaccard coefficients where the number starts from a lower number and grow to a higher number between 0 to 1. No attribute Jaccard coefficient. So we have added the Jaccard coefficient. So now we need to make sure that we do add here. So self dot Jaccard coefficient, and we also need to do same thing for validation Jaccard coefficient, because whatever we define we have to add. Now we made this method. So Jaccard coefficient, validation Jaccard coefficients, and it's getting this. So these two, and then this printing Jaccard coefficients, we need to use the validation Jaccard coefficient, and that should have this way. So we have added Jaccard coefficients and validation values of Jaccard coefficients, and then we have added same here, and after clear, adding that back to it. Okay, so let me define this. Okay, so that should be okay. The environment crashed, so I have to restart it again. RAM is really consumed at very high level. Now we are getting the results with the Jaccard coefficient and the validation of it. So we should grow from lower to higher value, because our objective is to get 0.99. It means the test as well as the original, they both are identical. So here is our plot after the 10 iterations. So now you can get an idea that you could use any of the model metrics and you can apply it. Now we need to learn to apply the diagnostics by using the two separate graphs. It means having the subplot and build the two graphs, and how we could get that also working in the same callback method. So I will keep this plot loss and I will create a new method. I just call it plot loss ex. So this is the extended version of it. This object which is instantiated from plot logs is the same, so that connection is still the same. We are not changing anything. Now our objective is to keep these two loss as well as the Jaccard coefficient, keep these two as well. So now we have 4 of these variables. I have cleaned up the plot loss ex and I have added a full code, and let me explain you everything what we have done. So the previously we had loss, validation loss, Jaccard coefficients, and the validation of that. We just collected the metrics from the log and added their value and rendered them in the plot. In this step, we have loss, validation loss, Jaccard coefficients, and validation Jaccard coefficient. And then we have created same way loss, validation loss. From the logs we are collecting these 4 parameters and we are saving them. And before we are clearing, first we have created plot.figure. We have created the subplots, 2 subplots, share x true, the sharing the value between these two, and we have made sure that the graph 1 and graph 2 are the plots in the subplot. Then we are clearing, and the graph 1 set y scale is log. Then in the graph1.plot, we are using the same loss and validation loss and with the legends, and then graph 2 same log y scale, and then we are plotting the same value of Jaccard coefficients and the validation Jaccard coefficients. So that way we could get the two separate graphs side by side in this matplotlib based subplot, and that is what going to render the results here. Okay, so it means that I could load this class. Now this plot loss object is instantiated. So I will take this method because I want to keep this graph. I will go ahead and run it. Our RAM is almost dead end. We have started the training process. And after the first epoch is done, it should create the plot with the two graphs. Left side loss and validation loss, and right side the Jaccard coefficients and validation Jaccard coefficient. Here you go. Left is loss, validation loss. Right is Jaccard coefficients, validation Jaccard coefficient. Here we will see the value is going to go from higher to lower, here from lower to higher. And because we have only 10 epochs, so we will have at least enough sample size for us to get our idea implemented related to diagnostics. Even when this plot is not very clean and clear, but I think by experimenting with these values, you could actually build a better graph. The training is completed for the 10 epochs. You could say that however loss and validation loss went down, and our Jaccard coefficients and validation Jaccard coefficients grew from lower to higher value. So conceptually, you have better understanding of how you could add the diagnostics in your deep learning process when you are using the Keras library, because the connection was in the training process by using the callbacks. So at this point, this part of tutorial completes. The model which we have downloaded at the local file system, we can actually visualize it directly by using the Netron. You can actually download the Netron on your local file system if that is what you would want to run, you would want to try. However, I could actually access the website directly here, drag and drop my model here, and that will open the model. And I will be taking this model and dropping it here. That's our model really look like, which we have created based on this whole network architecture. And if you expand this model, you can actually browse through step by step how we have created our model and which each attributes related to our model. As you could see, there is so much information available for you to process. And not only that, you can take this model and you can export it to a PNG, and this whole model is available as a PNG which you could share with anybody else. And by looking into this model, and this model image is actually detailed image of this model plot which we have created using the Keras utils. And same model can also be understood even more details by using the code when we have created our model network by following each line by line. Here, as we have created the convolutional layer, you could look into the parameters, the total number of filters, the kernel size, what kind of padding we have used, what stride we have used, what is our activation method. So this is everything what we have written in our this line. And the output of this line has been fed into the dropout layer with the dropout rate. And the output of this has been fed into this, and that's where it is ReLU, and then here the max pooling happened. But here you could say that this has been added into at the very last layer where the concatenation happened at the axis 3, and that is what we have done at this level where we met with some error, and then we fixed that error here also. So you can get an idea that this exact concatenation, what is really being happening, is actually the mirror image of this network. So I believe is that by visualizing your own network model, you can learn a lot more about others' model, as well as you could explain your network to somebody else. And after we have downloaded this model to local file system, we have loaded this model to the deep learning model visualizer tool, Netron. And looking into this model, we have validated that every line of code which we have written here to create our neural network, it matches this whole line of information with this piece of code. And whenever we have performed the concatenation as seen here, we have matched that with this concatenation with this original architecture to the line of code which we have written here. In the next part, we are going to apply a Python library so that we could get the activation results or the activation outputs as well as the gradients based on our training. So that's what we are going to cover in the next. We are also going to deploy the model which we have downloaded here that is currently on my local file system. So we will deploy that model at this Hugging Face space by creating a new space here like this, and we will deploy, and we are going to write the GradioBase UI for that model. And we are also going to use the Google Maps so that we could actually get a satellite image, remove the labels, and that's where you will be able to get a very good real actual image which has water, land, buildings, road, vegetation, and we could snap image like this, and we could apply our model which we have saved here to generate the prediction at Hugging Face. So there is a lot to learn in the part 3 of this same deep learning with satellite imagery series, and that is what we are going to cover in our third and the last part of this tutorial. Before we go, I just wanted to make sure that this Jupyter notebook has been saved to same place where other notebooks are with this local diagnostics name. And the Jupyter notebook is available here, where you could see that we have added the model plot. We have also added the local diagnostics subplot with loss and validation loss, including Jaccard coefficients and validation Jaccard coefficients. And the previous one is also there. And finally, it also shows that we have downloaded our model to the local file system. So we have covered lots of topic, lots of details, and lots of code in this second part of the video. I hope you have enjoyed the content. Thank you so much for your time, and I do appreciate it sincerely, and I'm looking forward to seeing you in my third and the last video with the same topic. Until then, thank you so much.